Hello, AP Chem. This is Mr. Weiss, and we are doing a video now for section 6.6 in the book. We're talking page 372, if you want to follow along. It's a big section full of a lot of ideas. I'll see if I can get through all of it today. If not, I'm going to have to split it up into 2 days. Okay? All right, get some notes out. We're getting ready to take some notes and follow along in the book. I will also say here, let me park this thing so you can see the whiteboard. I hope. Now you can see it. Okay. I'm going to give you a page number. Also, because the shapes I draw, Cheryl Smith has a good reference chart, and I'm going to give you that right away. Okay. So the reference chart for some pictures is page 392. So flip back and forth with me, page 392 and page 372. All right? So we're talking section 6.6, page 372, page 392 for the chart. What this is about is Vesper theory and how to use it. Okay? So it's spelled funny. VSE per theory. All right, you might as well know what it stands for. You ready? I bet you can guess the V, huh? Valence. The S going to be shell, I hope. Yeah, okay. The E is electron, of course. And the P is pair, like a pair of electrons. And the pair of electrons, and the R is repulsion. So what we're going to do is we're going to go through some shapes and some Lewis structures and go beyond there and more or less help you understand how to classify these suckers. The shape of molecules is called molecular geometry. That's what this is really about. And it's using the location of electrons to figure it out. Okay, so we're talking about molecule geometry. All right, molecular, that's probably a better way to say it, molecular geometry, and the applications of it. Why do we care what shape they are? Turns out it's a big deal, okay? How big? Water. Okay, I'll begin not with water, but with an idea, okay? Well, if I got one thing next to another thing, and that's it, that's pretty easy, okay? So if I've got Cl connected to Cl, right? We've done the Lewis structure for that, or else F2. And I got bop, 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 right? Because it also follows the rule, octet rule. Well, how are they situated? They're next to each other. So the shape is linear. And that is boring. So we're going to go on to something more interesting, okay? Instead of one thing by the other thing, we're going to put two things by the other. So what if I got like something like this? Do I want to label these? Not probably, but I'm going to look at what she did just to be consistent with your author. By the way, the angle between these two, 180. Not big surprise, right? On the AP, they ask you angles at times, okay? All right, let's put two things around one. So we got AX2 is how Cheryl says it. So you got two options, all right? Here we go. I could have something like CO2. So we're going to do some examples. And CO2, I don't know if you've done it yet. It's super important. It's got two double bonds, right? You're exhaling it right now. And as a society, we make way too much of it. And even though it's double bonds, it doesn't matter. I got two things around the central atom, two things around the carbon, an O and an O. And the idea with, now let's come back to the definition, valence shell electron repulsion theory. Okay, electron pair repulsion. Those electrons in the various bonds don't want to be near each other. So what they do is they don't want to, like here are the electrons and here's the C in the middle. They want to get as far apart as possible. Whoa. Okay, so they're going to be linear. Okay. Not always, but this one's definitely going to be linear. And we're going to have what? From here to here to here, this angle is 180 degrees. So we call that the central bonding angle or whatever you want to call it, okay? Yeah, and it's again linear. That's the shape. Here comes the biggie. It's something you use all the time, H2O. You might have done this with me in 10th grade, I don't know, but it's way important, and let's have a look at it. So I think I'm going to let you figure out the valence structure. I'm just going to give it to you now, but you can figure out why it's that way. You probably have to practice that with Cheryl in the book anyway. So it's got an O, and it's got a single bond to the H's. It's at an angle. We'll talk about why that is in a second. Do I want to put that here? Oh, phooey, hold on a sec. I might be screwing you up. Water might be down the line just a little bit. Yeah, water might be down the line. Let me see how Cheryl puts it. Okay, 492. All right, sorry about the dead time. I don't have my notes with me. I'm in quarantine. Negative, but there you go. At least I'm pretty positive I'm negative. Okay, let's come back to water. Okay, so if I got two things around one, pretty much the only possibility you got is linear because they want to be as far apart as possible. So with this AX2 type thing, we're done. Okay, let's go on to AX3. The A is the central atom. The X's are how many things around it. So A, central atom, X2, two things around it. Now we're going to do AX3. See if I can keep this thing up here now. Take a little less time to race. All right, so here we go, AX3. Let's do BF3 as our example. BF3. Now, boron, when it's done, it doesn't really follow the octet rule all that nicely. So all it does, frankly, is bonds 3 times. B, I got an F, I got an F, and I got an F. And then I got lots of dots around the F's because they follow the octet rule. So I got 2, 4, 6 plus the bonded pair of electrons and looking like that. So what's the deal? The deal is If I got three things around one, it sits in a plane, and if I spread them out, which I can't do by fingers without breaking them that far, it ends up being what's called a trigonal planar. And again, I'm going to check with Cheryl and see the word she uses. That's the word I've always used. Yeah, thankfully. Okay, so the shape is trigonal, like a triangle. Trigonal planar. And that means in the same plane, right? Well, what's the angle? Huh? The central angle is going to be how many degrees? It ain't 180, it's going to be 120, right? 3 times 120 is 160. So I got a 120-degree angle. Ute. All right. Now, what if one of them is not a bonded pair? So we're going to do SO2. Here's S. And for SO2, it's got a resonance structure, but we're just going to skip that. And we're going to say just one side's a double bond, the other's a single bond. And then I got an unshared pair on the sulfur. Make sure you got that. Yeah, you can see it. And then I got boom, boom, boom. And then the other one I need boom, boom. And I'm all done. I'm just following the octet rule. How do I know how to do that? Because I just add up to 8. And I know the bonds because I've done this a long time. Okay, now, how many things are on the central atom? Shaboom, boom, boom, 3. But it's not the same shape. You might say, but Mr. Weiss has got 3 things around it, 1, 2, 3. The molecular shape is only the molecules consisting of atoms, not including any unshared pairs like this little pair down here. So I got essentially 2 things around, and it's not linear, it's bent. That's the official name, bent. Okay? All right. What's the angle? 120? Yine. A little less than 120. You don't need to know the number. You just got to know it's a little bit less than 120. Why? Well, it turns out if I got an unshared pair of electrons, they have a lot more repulsion than the shared pairs in the bonds. I think it's because there's no nucleus out here. You know what I mean? There's no positive charge out here. Instead, it's just negative charge. So there's a little more push this direction and push this direction. So I'm going to write here just so we remember that more repulsion by, it's called a lone pair or an unshared pair. And what does she calls it a lone electron pair. Okay, so I'll go with that. Lone means like alone, so there's not another atom connected to it. Lone electron pair. Now do you see why I erased it? Why it's called Vesper repulsion, pair repulsion. That pair matters out there. So the angle is not 120, it's a little bit less than that. Again, you just got to say that. You don't have to know how much less. That's going to be down to studies. You don't have to do that. Good. That's the 2 shapes for AX3. It can be either trigonal planar or it can be bent. Now, you might say, well, what if it has 2 unshared pairs? Well, then it's just linear, right? If it's got 2 unshared pairs, then it'd just be 2 atoms next to each other, and that'd be linear, so that's easy. And I don't even know if that can exist. I don't know if I've seen that. Okay, let's do the biggie. The biggie, and I got to show you a shape for it when I'm back in the classroom with you, is 4 things around 1. And it's B or AX4. And the shape is called a tetrahedron. and it's way important. Okay, so we're talking AX4. And if I've got 4 things around 1, and again, I can only draw it like on a whiteboard, but it's not two-dimensional. Here it is. Here's methane, CH4. And I'm going to do it out here. C, H, 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 H. And that's it for two-dimensional. But that doesn't look 3D at all. It's actually like, it's like this shape. It's got like a lunar lander, 3 things on the bottom, and then 1 more up on top. And the picture she has is on page 372. Look where it says 4 balloons, and then you kind of imagine it, all right? Another way to draw it, 3D, if you like, is like this. I can also go C with 1 H on top, and then 2 over here, and then 1 in the distance. And the 1 in the distance I'm going to make smaller. Ooh, 3D, right? No big deal. So I make 1 and I make a tiny H like that. If that helps you envision it, great. And if not, well, I'm sorry. There's other ways to write it with little shadings and stuff, which I don't really like. She has that way of doing it. And now we're looking on page 374, by the way. Hey, there's a pretty good picture of a tetrahedron. Check out page 374, all right? In her little chart there, it's not bad. Okay, so there's methane. So the shape of that is tetrahedral. So the geometry, molecular geometry, is tetrahedral or tetrahedron. What is she like? I'll go with what she says. She says tetrahedral, which is what I like too. Nice when you agree with your author. Where did I drop that black? Nowhere. Here it is. Okay. Let's do pH3. pH3. It's got 8 electrons. I'll do it out with you just to remind you. How? It's got 5 from P, 5, not 8. Okay, it's got 8 valence electrons, okay? So 5 from P and 1 from each of the H's. So pH3, 8 electrons. So put the P in the middle, put the H's around it, and make single bonds. And that takes away 6. I got 2 more, and I got to put it on the P to satisfy the octet rule. And there's your 4 things, right? Remember, it's AX4. 1, 2, 3, 4. I got 3 atoms around the central atom and 1 unshared pair. All right? 3 atoms and 1 unshared pair. So what does that mean? Got to back up a sec. The tetrahedral angle, whether I draw it up here or down here, even though it may not look like it, it's over 90. Maybe I'll do it on both of them. And it's, if I actually have it, it's 109.5. Memorize that number. Sorry, memorize the tetrahedral angle, 109.5. You need to know it for the AP test. I'm writing so sloppy. There, 109.5 degrees, okay? There's 4 angles. Each one is 109.5, right? Central angle out to HH, central angle out to HH, HH, HH. It's all 109.5. Again, it doesn't look that way because it's a 2D blackboard. Look on her picture and you get a little better idea on page 374. Okay, tetrahedral picture. Well, what's going to happen? Well, one of these suckers is an unshared pair. What's it going to do? Needs more elbow room. It pushes. So it's going to push this way and this way. So the angle will not be 109.5. It's going to be a little less than 109.5. How much less? Well, you don't have to know. It's about 107, I guess, but you don't have to know that. You just got to know that it's less. However, what you do got to know is the shape. So put your, turn to page 374. Put your finger on the top here and cover that up. So the shape is just what's left. 3 atoms down below the central atom. It looks like a little lunar lander, a little pyramid. And that's what it's called. It's called a trigonal pyramid. Oh, so kind of like that, all right? Trigonal pyramid. So you can tell what I'm doing each time. I start out with all atoms for the AX2 or AX3 or 4 or whatever. And then I start throwing in unshared pairs. So there's one unshared pair. So now it's just got the lunar lander look, trigonal pyramid. And now we're going to throw in a second unshared pair. So I'm going to race over here. And now we're ready for water. So here we go. H2O. Here we go. So I got O bonded to 2 different H's. And I got 2 unshared pairs on the O. Well, that makes 4 items, believe it or not. 1, 2 atoms, and 1, 2 unshared pairs makes 4. So it's still in the AX4 type of thing. But what's left, man? Well, for starters, these things really repel. But the shape, you can guess already. What's the shape going to be for water? Starts with a B, rhymes with ends. Bends, right? So not big surprise. Water's bent. The reason water is like it is because it's bent. It has a lot of unique qualities because it's bent. We're going to find that out later this section. And the angle is no longer 109.5. It's no longer less than 109.5. It's much less than 109.5, okay? So an angle and Cheryl gives you that. I don't know, it's like 104 or something, but again, you don't need to know that. You just got to know it's a lot less. Why? Because these suckers repel, man. These unshared pairs, they got no nucleus around. All they do is repel each other. They want to be far from each other and the atoms, the electrons and the bonds as possible. So these guys push quite a bit. Notice we only want the bond angle of the atoms, not all the way around the other side. You could do like 360 minus 104, but nobody does, okay? So it's the angle that's left there that they want on the AP. Huge. That is the tetrahedral. We're ready for AX5. So I'm going to race and put that sucker over here. By the way, all the geometries I'm showing you, they work for bigger molecules too. Bigger molecules like DNA, okay? They're just combinations of these simple geometric shapes put together. Okay, so the stuff you're learning from me is powerful. It goes for bigger stuff as well as relatively small molecules that we're starting with. Okay? So I'm not being wimps with you. Okay, AX5. Okay, for AX5, I got a nice way to show it. And it goes like this. It's like a triangle, and then it's got something above it and something below it. So let me show you that. The general shape is like this. And then now put a stick through the middle. Ready? Like a piece of pie with a string through it. Except the piece of pie is an equilateral triangle. It's not really pie shaped. So there's an atom here, 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 and here. Where's the central atom? Right in the middle. Let's put that in red. Okay? So if you like, you can imagine that. Okay? So a rectangle, a triangle, equilateral triangle, and an atom above it, an atom below it, and atom at each of the vertices of the triangle and above and below it. We call it the pole positions. North pole, south pole. Okay? Good. Let's make them all atoms. So I'll just give you one. Let's do N and F5. Okay, so example N F5. So we got what? We got 7 valence electrons from the F, but we got 5 of those, so really we got 35. We got 5 from N, so we got 40 electrons to play with. Here we go. Put the many around the few, right? So N goes in the middle. Put a bunch of F's around it. F, F, frickin' F, F, F. Make all single bonds. Can you tell this is going to be an expanded octet? Ooh, shame on me. It is. So let's make this P. This doesn't exist. My mistake. Okay, if it's an expanded octet, nitrogen is too small to hold all that. It's just too little. But P will work. So let's make it PF5. Sorry about that. Okay, so you got single bonds all the way around. You got 5 of them. So we're going to take away how many electrons? 10, right? 5 times 2 is 10. So I got 30 left. Fill out your outer electrons in your outer atoms first. Okay, so we got it. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Da-da-da. Isn't math beautiful? It worked. So what's the shape of this? Well, it's like two pyramids, isn't it? So we're going to call it a trigonal bipyramid. And think of that shape, trigonal bipyramid, right? Where's the bi? One up here and one down here. I won't fill in the whole thing, but you get the idea. So that's the shape. Trigonal bipyramid. Huge. With a trigonal bipyramid, you got 2 types of angles. All right, I better draw this again, and I got to draw it bigger so you can get the angles figured out, okay? All right, so here we go. I'm going to draw this thing. So here we go. Shaboom, shaboom, shaboom. Okay? So let's say here's our central atom in the middle. And let's make then a pole position and a pole position below. Okay. The angle between the vertices of the triangle, if it's an equilateral triangle, is what angle? So from here to here to here is what? I hope you said 120 degrees. Kind of like the trigonal planar, right? 120, 120, 120. But there's a second thing going on. Okay, here it is. Let's say my hand is the equilateral triangle. Now, here's the pole. I got an atom up here. What's the angle between here to my hand? 90 degrees. So I got another angle, which is from here down, and that's 90 degrees. So I got two sets of angles. Don't worry, not a lot of them have this, but that does, okay? All right, hang with me. Hold on tight. Okay, so I got 5 things around one, and all of them are atoms. Let's change it and make one of them a what? An unshared pair. So we're going to do a little example, which looks like this. We're going to do, I'll just take her example because I'm without my notes. So we're going to do SF4. And it's going to look like this. I got an S. And I got 4 things around it. Now I got to think about it. Where can I put the unshared pair? So I got, well, okay, you don't know that yet. I got 4 atoms bonded, and I got 1 unshared pair. Where can I put that where it'll take up, remember it repels, so I want it to have the most room. Do I want it at the triangle, or do I want it up here at the 90? Well, it turns out I want it up at the 90. I want it at the, no, I said that wrong. Turns out I want it at the belt. I want it at one of the spots here, one of the 3 vertices of the triangle. The angles there are bigger, 120. That's why. So I'm going to put it here or here or here. So I'm just going to make that up. We'll say it's there. And then I'm going to put another one like there. There's an F. There's another one that's an F. Another one that's up here, that's an F. And then down here, that's a F. So what that means is one of my little triangles, if I go over here, one of my little atoms has become an unshared pair. Like that. What does that do to the angle? Remember, that sucker repels more. So what's going to happen to the angle here? Well, these angles are going to be slightly less than, what was it over there? 120, so a little bit less than 120. Not a lot, but a little bit less. And the other angles are still going to be 90. Right, 90 degrees. The other angles from the pole down to the equilateral triangle at the plane. You really got to think 3D for this, don't you? So pole, equilateral triangle, pole. Here, that's where the unshared pairs go because they can take up the most room because of those big 120-degree angles. The shape, now, ready? Make this thing fall over. Boop. So it's going to be like this shape. And. Actually, we're going to make it go this way. And then we're going to go in. Does that look something from your childhood? It's called a seesaw. I can't remember the German word for it. and that's a seesaw shape. So that's my geometry. A seesaw shape. Weird but true. Let's continue. You know what we're going to do, don't you? We're going to add another unshared pair. So that was with one unshared pair. And again, don't get all weirded out. It's all on page 392. Cheryl's designed it very beautifully for you. Page 392 has a great chart for you. Okay, so we're down at, we're down at seesaw. Now she says it's less than 90. I've not really heard that, but maybe she's right. Would it have to be less than 90? I don't actually see why. I'm going to leave that as 90. Maybe I need to consult with her. Okay. I got to think about that. Okay, let's do the last one. So here we go. The last one for AX3. So we're going to put one more unshared pair on this thing. And we're going to call it, let's just do the one she does. So CLF3. And so what I got is I got a CL. I'm going to just skip to it and show you. CL's in the center. And I got two unshared pairs. So I'm going to put one here and one here. That's on the equilateral triangle. So I only got one sticking out here yet to an F. And then I got the pole position still there. Shaboom, shaboom. And of course, the angle is certainly less than 180, isn't it? 120. Actually, no, we don't have any 120s anymore, do we? The 120s are gone. Why? Because the atoms are gone, right? Now the only angle is 90. Cheryl says it's a little less than 90. Maybe I should do that. I'll follow her. She's probably checked this out. At any rate, the general shape looks like a big T on its side, doesn't it? Okay, we're almost done with this. Here we go. Let's throw in one more unshared pair. You know where it's going to go. It's going to go in the pole position. You probably guessed the shape of it. And I don't know a lot of these, so I'm going to use the one she uses, XCF2. Whoa. You thought xenon didn't make any compounds, right? Because it's a noble gas. Surprise. Welcome to AP Chemistry. So it's got three unshared pairs of electrons and two atoms. So the atoms go at the ends, F above, F below, what I call the pole positions. And then I got 1, 2, 3, and all three of those go in the equilateral triangle shape. So you know what? The angle is exactly 180. There's no way to repulse that because it's coming from all three sides. And the shape starts with an L, means straight, linear. Ta-da! Congratulations, you're almost done. One more shape. Stay with me. Okay, the next shape is, you guessed it, Chester, AX6. And it's the last one. Whew! I find it easier than the last one we did, okay? And it looks like this. The middle is like a square. And then I got a pole going up and a pole going down. And I also got atoms at each corner. And I got the central atom in the center, not surprisingly. So it's like a square, and then I got something going up and something going down. You can maybe guess the shape already, okay? And here is the sucker and what it is. So we're going to do SF6. We're going to do her example. And so we got S, we got an F above, we got an F below, we got an F to the side, we got an F to the side, we got an F to the side, we got an F to the side. And all the angles, if you think about it this time, are really easy. They're all how much? 90. Just I did those in blue. So all the angles, although they don't look like it here, they're all 90 degrees. And the shape is called a bipyramid. Oh, well, actually, it's not anymore. Used to be called that. There's a special name for 6 things around one, like this, and it's called an octahedron. It's because it has 8 faces if you draw the structure. So think of it. I got like a pyramid down below with 4 sides. I got a pyramid up above with 4 sides. 4 plus 4 is 8. So octahedral, even though it's only got 6 atoms around the central atom. All right, sorry, it's a little wacky. That's the way it is. So an octahedral shape if all of them are atoms around the central atom. Okay, 90 degrees, and that's your shape name. Let's continue. Next one, BRF5. And as you could guess it, we're going to do one unshared pair. And now, because it's all 90 everywhere, it doesn't really matter where we do it. So we're going to do it to make it easier for us. Okay, here's the BR. And I'm going to say my unshared pairs down here. So what I'm going to do now is put F's out at the corners. F, 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 F. And one F going up. That's the pole position. So can you imagine my drawing here? Cover the bottom one, that's an unshared pair. So essentially I got this, don't I? Well, all right, I'll try again there. And I got this. So the shape, ready? The shape is a what? A square pyramid. Why? Because the bottom one is dropped out. We're going to put that this time at the South Pole, so to speak. And if it's at the South Pole, then all that's left up here is a square and then some lines going up, imaginary lines going up. And the shape is a square pyramid. And I'd say all the angles are 90. And what does she say? She say they're less than 90? Yes, she does. She says they're all a little bit less than 90. So the angles, because of the pushing of this thing, a little bit less than 90 degrees. I'll go with Cheryl. She's pretty smart. All right, we're getting there, folks. We're getting there. We're so close, I can taste it. Okay, so we've got, we put in one unshared pair. Now we're going to put in 2. And we're going to use, oh God, does she have to use that one? All right, so we're going to do ICl4 minus, oh God, ICl4 minus the tetrachloroiodate ion. You don't need to know that. Okay, so we got, turns out we got 2 unshared pairs. And we got 4 atoms. around the center. I'm writing this because I feel like it's getting a little out of hand, you know? Let's help ourselves keep track. So what we do is we got the I in the center, and we're going to put a CL out here, out at the edges of the square, all right? And then up here I got an unshared pair and another unshared pair down there. Oh, I can put it closer. So all I got left to cross off the bottom is a square, and it's called square planar. Square planar, that's the shape. Okie dokie. Right. Square planar. Are we done? We're done with the shapes. Hooray! And again, page 392 to help you review them. But now we got to figure out, why do we got to know this and what good is it? And do we got to memorize how to do this? Yep. Okay, here's the deal. It has to do with electronegativity and whether there's a dipole or not. And it totally depends on the shape. So that's why we got to know the shape. Let's do one. Hope you caught up. Here we go. I'm going to take the whole board and start all over. So we're going to call this using geometry to predict if there's a dipole or not. First one up, CO2. All right, we agreed it was linear, right? Well, there are some dipoles, okay? Who's more electronegative, O or C? Remember how to do that? The closer to F, the more electronegative. O, yeah, O. O is. So what that means is, in terms of dipoles, I'm going to show the electrons being pulled towards the O's. So I've got two what are called bond dipoles, but the two bond dipoles cancel out. So effectively, there's no overall molecular dipole. You could say no overall dipole, no molecular dipole, or just no dipole. I'll say molecular dipole for this. Let's do another. Let's do CH4. All right, we agreed that CH4 is tetrahedral. And I made it kind of like this. I said, I got an H there, I got an H there. I got one back behind here that's smaller, and I got an H up above. Turns out C is a little more electronegative, if I remember right. Anyway, it doesn't really matter. But I think C is. So I got little dipoles all pulling in. But you know what? If you can do this and imagine it three-dimensionally, it's really, really symmetric, all those bond dipoles. Once again, all four bond dipoles cancel out. There's no net dipole for the molecule. Okay, so bond dipoles cancel. So no overall or molecular dipole. Or we could say it's a non-dipole. Ready? It's a non-dipole molecule. Now, look to the future. Why is that important? It makes the connections between molecules really weak. Connections here, really weak. So methane, that's what this molecule is a gas. Connections here between a CO2 and the next CO2, weak. Back up. So it's between a methane and the next methane. Those connections are weak. So it's a gas. So weak connections between molecules if there's no dipole. So both of these are gases. That's why they're both gases at room temperature. That's important. If CO2 was a liquid, you'd be dead because it would fill up your lungs and you'd be gone. If methane was a liquid, it would have to be administered to burn in stoves a whole lot differently, okay, instead of natural gas. I'm not going to fool around. We're going to do the most important one of all. It's water. Remember the shape. It's bent, right? I got O, I got H, I got H, and I got a couple of, so I got four things around one. Initially a tetrahedral, but since two of them are unshared pairs, we say the shape is, again, bent, right? Now let's draw some bond dipoles. O is more electronegative than H. So the bond dipoles go like this. One this way and one this way. Ooh. If I add those up, do they cancel? No. What that means is water has a more negative side and a more positive side. Water has a molecular dipole. It likes other waters, and it's a liquid because of that. That's hugely important. So water has in fact, a very strong dipole. The bond dipoles don't cancel, right? There's nothing going down to cancel those, right? There's no pull of electrons from up above because there's no atoms up there, right? It's about pulling the electrons. Remember, electronegativity is who hogs the electrons. Well, O is a bigger hog, so they get pulled this way. Cheryl will also show this, and some other people will, with a delta. So another way you'll see this is O with a delta negative and a delta positive. I don't like that. I don't want to fuss with it, this stupid delta letter. But you know what? If you want to do it, do it. So if you see it in her book, that's what she's saying. It's just a dipole, minus on one side, plus on the other. Okay? So anytime molecules are symmetric, the bond dipoles cancel. If they're asymmetric, then they don't cancel, and you get a leftover dipole moment. That's another name. So I can also say this has a dipole moment. Again, not terminology I use so much, but books use it and the AP test uses it. So yeah, there's a dipole moment there, okay? Ute, let's do one more, and you're going to do a bunch of these in the book to help practice on them as well. So let's have you do, well, you're going to do a bunch. You can't do it with me now. Okay. I think I'm going to wind it up here, so we're not going to get through the whole section. Okay, so last example is one we already did. Ole preole. So let's talk about ClF3. If you remember, this thing had two unshared pairs there. It's on the equilateral triangle. The third part of the equilateral triangle is an F, and then I got an F here at the North Pole and an F connected at the South Pole. Well, what does that mean? Well, let's see. F's the most electronegative of them all, isn't it? So I could put a little arrow here, so the electrons are pulled more that way, they're pulled more this way. Oh, those look like they cancel, but the third one doesn't. Check that out. So the molecule has a dipole. It's more negative on what? This side, and more positive over here. Or you can use that darn delta thing if you want. So this sucker has a dipole. Or if you like, dipole moment. Just to use the new terminology, okay? Yippee skippy. All right, that takes you up to page 382. No, 382. I'll do the last part in a future video because this is really running too long. I don't want to overwhelm you. So we're going to do the part about intermolecular forces, which is a huge topic, and hybridization, which is an important topic too, to end that chapter. You can try them if you're that far anyway, but if not, stop a little before that. So I'll do another video with you soon. Good. Hit the books, and I'll be in touch with you. All right, be well.